Hi guys, I'm just making this video so that hopefully you can see why polar form is useful to us. So if you can't remember, just as a recap, polar form is when we write a complex number z by writing the modulus out the front, and then we have cis, which stands for cos plus I times sine, and then we have theta, which is the argument for that complex number. So what that means is if we're graphing this on the argand plane, z looks a bit like this. The length of that arrow is the modulus of z, and then the angle from the positive real axis tells us that value theta. So first of all, there's a few properties of cis theta which are really handy, and there is a proof for this in your textbook. I'm not going to go into the proof in the video, but I'm just going to show you what the properties are and then why they're useful. So the first property is that if you multiply two cis values, so cis of theta and cis of phi, then we can actually combine that into one cis of theta plus phi. So this is basically saying cos of theta plus I times sine of theta. If we multiply that by the cos of phi times I times sine of phi, that's the same as cos of theta plus phi plus I times sine theta plus phi. So this comes out of our trig identities, but that is a really useful little thing there. The second one is that if we do something similar, but instead of multiplying we divide it, then the angle that's on top, we use that, and then we subtract the angle that's on the bottom. So cis of theta divided by cis phi is cis theta minus phi. And then the last property basically just says that the cis of theta plus 2k lots of pi equals cis theta. Now I should have actually added in there, this is where k is an integer, okay? So we're basically, what we're saying with this last one is if this is your value cis theta, if we then add on 2 pi to the argument, well, 2 pi is just a lap of the unit circle, or a lap of, a circle. So we're going to end up back where we started. So the cis of theta plus 2 pi is going to be in the same place. And then if we go around again, that's like 4 pi. So we're just going to end up in the same place. So the cis of theta plus 4 pi is going to be at the same spot. So no matter how many times we go around, or in fact, even if we go backwards by negative 2 pi, we're always going to end up back in the same spot. That's all that rule there is saying. And that rule does seem kind of obvious, but it will become really useful a bit later on. So I just suggest that you pause the video and just write down those rules in your book to start with. Okay, so let's have a look at some examples of how we can apply this. So first of all, what we're going to do, we're just going to look at simplifying a couple of expressions. So the first one here is cis of pi on 6 over cis of 7 pi on 6. So using our rule that we saw on the previous slide, what we can do here is just subtract those two angles and put it into the one cis. So that's going to be the cis of pi over 6 minus 7 pi over 6. And if we do that subtraction, we'll see we get cis of negative 6 pi over 6. Now you might notice that simplifies down to the cis of negative pi. Now if we think about what that means on the argand diagram, well, we started with the cis of pi on 6. Notice, by the way, at the moment I've just got a modulus of 1. So I haven't brought in the modulus yet. So we've just got a modulus of 1. So here's cis of pi on 6. Okay. cis of 7 pi on 6 is over here. That's 7 pi over 6. And then once we combine the two of them, we end up at the cis of negative pi. And if we think about what that means to be at cis negative pi, well, if we think, okay, now we're right on the real axis here. So if the modulus of that number is 1, then what we're actually at is the number negative 1. So we can simplify this that we started with, which is quite complicated, just down to the number negative 1. Okay, let's have a look at this second example. And I do suggest I copy this diagram, this example rather, into your book along with the diagram, because it is useful to be able to look at that. So maybe just pause the video if you need to and copy that down. And then we'll have a look at this second example. So now we've got the cis of 23 pi. Now, I don't know about you, but I don't want to really think about what 23 pi means. But if we break that up a little bit, if we think about the nearest even number below 23, we can say, okay, this is the same as 22 pi plus another lot of pi. Now, this sort of comes down to that last rule there. 22 pi, that's like our 2k pi. In this case, k would be equal to 11. So we're saying, 22 lots of pi just takes us around the unit circle 11 times. So we end up back where we started with. So really, what we're going to end up at is the same as just the cis of pi. Now again, if we go up to a little diagram and think about what that means, well, if we go around by pi, again, there's a modulus here of 1 that isn't being written. So this just has a length of 1. Well, wouldn't you know it, we've actually ended up back at the same spot. So weirdly enough, those two examples end up with the same answer. Okay, so I'd suggest that you write that example down as well. And I'm going to make a part 2 of this video. And so watch this one, and then there'll be some questions to do, and then watch part 2 and do the questions from that as well. Okay, thanks for watching.